All right, well, this is lesson 1.2, but I do have one little thing that was technically, as far as your notes go, this example is still 1.1, day 2. And I think we have a couple minutes here. It's worth our time. I just want to review the basics of elimination to solve a system of two equations. Again, this should technically be lumped into 1.1 on the second day, but we'll take a look here, okay? A system of two equations, all right? If I were to look at it graphically, which I don't want to spend most of our time on, a system of two equations, the solution is that xy coordinate of where the two intersect, all right? But I want to focus here on just some algebraic techniques to find that. This is an example using elimination where I'm going to add these two equations because I can see when I do that, these y variables are going to be eliminated. Okay, y plus negative y is 0. Now I have to do it to all three of my variables. X plus 2x is 3x, and 5 plus 1 is 6. This is where the technique takes its name, and it doesn't say it on here, and if you wanted to label this, this is the technique of elimination. Substitution is another method that, as time goes on, when the work that we're doing calls for us to solve a system of two equations, we'll come back and review a little bit. But right now we're just looking at elimination. But that eliminates a variable, gives me one equation with one unknown. And I see here that my x-coordinate for the solution point where these two lines intersect is 2. And now I can head back up, and in either equation, I'm just going to put it back into the first because it looks like it's going to be even easier than the second one to solve. 2 plus y equals 5. And I could subtract 2 from both sides, and in one single step I can see that y would have to be 3. And the coordinate points where those two lines intersect are 2, 3. That is x equals 2 and y equals 3. Okay? That's a technique that I know you've seen before. And again, if I wanted to check it, I could make a more accurate sketch than just the little visual diagram that I wrote out explaining that two lines their solution to a system of two lines is that point where they intersect. I could get more accurate and make a really accurate graph, and that would be one way to kind of verify my answer, to see on the graph, are these really the coordinate points where these two lines intersect. All right. Again, that's really part of 1.1. I covered it here. So there it is. That's something to just have kind of on your radar, solving a system of two lines. Okay, so this is actually 1.2. The topic is slope. All right. We've talked a little bit about lines. All right, we're going to talk about parallel lines, perpendicular lines, lines that are neither parallel or perpendicular. All right. Remember, the slope applies to any two arbitrary points. We mathematicians are just known for our outside-the-box thinking. So we had to think of two names for the 2 points that any 2 points. We went with point number 1 and point number 2. Like I said, leave it to the mathematicians to be really creative. Point 1 and point 2. Any 2 points on the line, subtract the y's, divide it by the difference between the x's. That gives you this very, very important ratio called slope that tells us the steepness of the line. 4 types: a positive slope, a negative slope, a slope that is 0, and an undefined slope. Okay? With these 2 cases, remember, they have slightly different equations. A horizontal line has a slope of 0, and its equation is just y equals a constant number. A vertical line has an undefined slope, and its equation is x equals a number. Okay? Be as specific as possible if you're referring in a problem to one of these 2 equations. Sometimes I've seen students get a little bit messed up on saying things like, well, this line has no slope. And there's been times where I've seen that students mean they're talking about a horizontal line, which has a slope. it's 0. Okay, that it's not correct to say that that has no slope. Other times they're referring to the vertical line, which its slope is undefined. Stick with saying a horizontal line has a slope of 0 and a vertical line has an undefined slope. You won't go wrong if you stick with those two terms. All right, so we got slope-intercept form. Okay, that's a wonderful little form to use. We took a little peek at this, I believe, in the first lesson. Its slope, it's m, its y-intercept is b. Now this would be a place where we could go through the work. I'm not going to do it. I'm going to refer you back to 1.1a. We worked through here and saw that in general form, if we go off of these coefficients a, b, and c, the slope is the opposite of whatever a is divided by b, and the y-intercept is c divided by b. All right? Parallel lines have equal slopes. Okay? We can say equal because slopes can be measured with a number, and equal only applies to numbers. And a slope comparison is really the only way to tell if two lines are parallel. Okay? Going back to what I was saying up here with slope-intercept form, oh, is it fantastic to check. Are these two lines parallel? They absolutely are, because for both of them, they have a slope of 3. And in slope-intercept form, it's just sitting there, right there for us to see. Both lines have a slope of 3. Over here in general form, okay, I could stick with the fact that, you know, for these two slopes, I'm going to call it slope number 1 and slope number 2. A is 6, so I'm going to say negative 6 over B, which is negative 2. Okay, and now for slope number 2, negative A is 6, but B is 4. Okay, so if I clean these up a little bit, I see the slope for line number 1 is 3. The slope for line number 2 is negative 3/2. Okay, a little bit more work to do in general form. It's not horrible. Okay, I think a better way to think about it is general form to find this information. It's okay. Slope-intercept is just really, really nice. Okay, really fast, really easy. Leaves us with a little bit of work to do, but if you can remember this, it's not too much work. Okay, it's not too much to figure out. All right, perpendicular. Okay, perpendicular lines don't have equal slopes. They have opposite signs, and they are reciprocals. They are negative reciprocals of each other, and their product is always negative 1. I think it's kind of a bizarre relationship. It's just the way it works out. Okay, you let's see, if we had, you know, the slope of line number 1 was 2/3, and we know line number 2 is perpendicular. That means its slope would be negative 3/2. And you could always check when you have that fraction and you flip it and switch the sign, you will see this element always follows. Okay, fractions that are negative reciprocals have a product of negative 1. Okay, kind of an interesting little relationship. It's just the way it works out. If you want to convince yourself of it, find some graph paper, graph some lines that are perpendicular, measure their slope. It's kind of a quirky little relationship, but it just naturally occurs. Okay, we've got this line in general form. We're going to determine its original slope. I'm going to use our little shortcut. Here I see that A is 2 and B is negative 5. So I know that its slope is negative A over B, which is 2/5. Now the slope of the line perpendicular, okay, I'll just call that M sub P, for M for slope, P for perpendicular. Here's where I just go to my negative reciprocal. Negative 5/2 would be the slope of any line that is perpendicular to that line that was given to me in general form. Okay? That will actually do it for our quick, relatively brief discussion of slope. In the homework, we'll practice how to calculate it. practice identifying if lines are parallel and if lines are perpendicular. But we'll call it quits there.